Welcome, math friends. We're going to talk about logarithmic functions today. And in order to really get an understanding of logarithmic functions, you need to understand one-to-one functions, inverse functions, and exponential functions. A one-to-one function is a function where every x takes on a specific y and every y takes on a specific x. There's no crossover. Remember, a function is where for every x, there's only one y, but this is also for every y, there's only one x. And a one-to-one function can be mapped, making sure that your x's and your y's are unique. So when I wrote f of x1 does not equal f of x2, when x1 does not equal x2, if you have the point 1, 2 and 2, 2, that's a function, but it's not a one-to-one function. A function does not violate the vertical line test. A one-to-one function does not violate the horizontal line test as well. We've talked about inverse operations. Multiplication and division undo each other, addition and subtraction undo each other, square root undoes each other. Inverse functions, rather than inverse operations, are functions where the domain and the range switch. You can also, in an inverse function, use the line y equals x. Functions are reflected over the line y equals x. Let's use that idea to graph a logarithmic function based on an exponential function, since exponential functions and logarithmic functions are inverses of each other. Here's the line y equals x. It goes through 1, 1, 2, 2, 3, 3, and so on. This is going to be our reflection line. Recall that we did the function f of x equals 2 to the x in the exponential function video. That went through the points 0, 1, negative 1, 1/2, negative 2, 1/4, 1, 2, and 2, 4, and also 3, 8. Let's graph that. Using the idea that the exponential and logarithmic functions are inverse functions of each other, and the fact that inverse functions have the domain and range that switch, I'm going to swap the x and y's for this exponential function. Instead of 0, 1, we're going to get 1, 0. Instead of 1, 2, we're going to have 2, 1. Instead of 2, 4, we're going to have 4, 2. Instead of negative 1, 1/2, we're going to have 1/2, negative 1. And instead of negative 2, 1/4, we're going to have 1/4, negative 2. And if you imagine folding the paper across that orange line, you see that the blue and the green graphs actually do line up. A logarithmic function is the inverse of an exponential function. Now, I don't necessarily know off the top of my head what log base 2 of 8 is. When I look at it and I say evaluate, I'd have to rewrite it in exponential form to know that that would be 3, because 2 to the third is 8. It's much easier to compute exponential things than it is logarithmic. So the best way in which to evaluate a log is actually to rewrite it as an exponent. Same with graphing. Notice the domain. If we look at the green graph and the blue graph, let's imagine the exponential function and think about what the domain and the range were of that function. And the fact that the range and the domain switch, that's going to help us determine the domain and the range of the logarithmic function. And if we look at the blue graph, we notice that it's getting larger and larger without bound, but it's going towards negative infinity as it approaches the y-axis. So it's just going to keep getting more and more negative, which means that the domain then goes from 0, doesn't include 0, but from 0 to positive infinity. In interval notation, that would be 0 to infinity. And in set notation, that would be the set of all x values such that x is greater than 0. And 0 is not included, remember, because nothing to the exponent got us to a negative. Anything to an exponent either gave us positive large values or positive small values. The range then takes on the domain of the exponential function, which was all real numbers, because I can go the function's going to get bigger and bigger, and the function's going to get smaller and smaller. So the range is going to take on all values, which should either be the symbol for all real numbers, negative infinity to infinity in interval notation, or the set of all y values such that we go from negative infinity to y to positive infinity. Let's now sketch a logarithm by hand. Let's say I have log base 2 of x. I'm going to determine if I'm plugging in any x value that's going to help me. Now, I know that my domain has to be positive numbers, so I can't go from -2, -1, 0, 1, and 2 like I normally do, but I could say 1, 2, 3, 4 or something, but knowing that I'm dealing with base 2, if I want numbers that are going to work out kindly, I probably want to stick to multiples of 2. I could say 1, 2, 4, 8, 16. Let's just throw in one that doesn't work out very friendly. Let's just say I have 3, just for fun to see what happens. That's saying the function at 1 is log base 2 of 1. The function at 2 is log base 2 of 2. The function at 4 is log base 2 of 4. The function at 8 is log base 2 of 8. And the function of 3 is log base 2 of 3. Again, I don't really know what those are off the top of my head, but I could rewrite them in exponential form to say 2 to the y is equal to 1. 2 to the y is equal to 2. 2 to the y is equal to 4. 2 to the y is equal to 8. And 2 to the y is equal to 3. Well, 2 to the 0 power is 1, which means that this is the point 1, 0. 2 to the 1 is 2, which means this is the point 2, 1. 2 squared is 4, which means this is the point 4, 2. 2 cubed is 8, which means this is the point 8, 3. But then I have 2 to something that gives me 3. And I don't really know what that is. That's not going to turn out to be a nice even number. I would need to use my calculator for this. I would need to actually do maybe the change of base formula to say what is the log of 3 over the log of 2 or natural log to be able to actually calculate this to get some decimal. Using my phone, I was able to calculate log base 10 of 3 is around 0.477, log base 10 of 2 is around 0.301, and when I found their quotient, I got 1.585. You do that directly into your calculator, but this is about 1.585. Not very accurate on a graph. It's not going to be great to graph. It's going to be an approximation. Now, I'm going to graph these points. Same graph as above, but notice since I didn't pick any x values as fractions, I don't really have anything past that 1, 0, and it would be helpful if I had some. So just as a reminder, when you're graphing the log, maybe you want to find those negative exponents to determine what would happen, what our values would be down smaller. So we're getting closer and closer to 0. We determined that the range was going to be all real numbers, but the domain was going to approach 0 but never get there, which means I have an asymptote of x equals 0. I can transform the logarithm. Inside the function would be inside the logarithm. I encourage you to watch the transformation video so you understand all of the different ways that we transform, but inside the function, which are the horizontal transformations, is actually inside the logarithm statement. Outside the function is outside the logarithm statement, and these are vertical transformations. Notice the log of parenthesis x plus 2. That means the plus 2 is on the inside. That's going to shift our graph 2 to the left. And then I have log of x plus 2, which is actually going to shift log of x up 2 vertically. I hope this was helpful. Thanks for watching.